Welcome to another one of AMS Weather Band's webinars for our webinar series. Today it is a force to be reckoned with, how large storm complexes rock the summertime landscape, with our panelists, presenters David Stensrud, Becky Adams-Seelan, Ruby Lung, and our moderator, Robert Howes. We got a lot of really cool information for you, so let me just really quickly get the housekeeping out of the way. If anybody has any questions, please put them in the Q&A option at the bottom of our screen. We'll collect all of the questions that you have there so that we can have one-stop shopping place to go to so that we can make sure all of your questions are addressed. And we will also have some dedicated time at the end of our presentation to answer any of the questions that you post up there. But during the flow of our event, if there are any questions that come up that seem to fit in with the flow of the event, we will make sure that we address those as well. But enough of me. Now I would like to introduce you to today's presenters. So thank you, David, Becky, Ruby, and Robert for joining us this evening. Our moderator for today is Robert Howes, who received his BS at Texas A&M in 1967 and PhD from MIT in 1972. Robert was a professor of atmospheric sciences at the University of Washington, go Huskies, from 1972 until his retirement in 2017. He has studied MCSs since the iconic field program of GATE in 1974, when he discovered that the stratiform regions of MCSs accounted for around 40% of tropical precipitation in the GATE region. Since then, he has participated in many field programs of observing MCSs in the tropics and mid-latitudes with radar, aircraft, and ships. He has received the highest research award of the AMS, the Rosby Research Medal, and the highest research award of the Royal Meteorological Society, the Simmons Medal. He authored the book Cloud Dynamics, the second edition of which was published in 2014. And so with that being said, Bob, I turn the floor over to you.
Thank you very much, Gideon.
Thank you.
I am going to now share a screen with everybody. Okay, when I was asked to do this webinar today, my assignment was to get everybody involved by answering what seems like a simple question, but it's not really simple. What is a mesoscale convective system? We talk about them all the time. What are they? Well, really, they are a member of the family of what we call convective clouds, which are the clouds which form as a result of buoyancy and acceleration, usually from the boundary layer. This picture shows the simplest and smallest member of the.
Excuse me, Bob. I'm sorry to interrupt, Bob, but we're not seeing your slides. We're still seeing you. There we go.
How's that? I am sorry. Do you want me to just back up? Let me back up and start over. I apologize for that. I just didn't hit the button.
No worries.
Yeah, my assignment was to answer the question, what is a mesoscale convective system? Which, as I said, seems like a simple question, but it's not really so simple. The mesoscale convective system is really a member of the convective cloud family. The convective clouds are those that arise from buoyant acceleration of air parcels, usually from the boundary layer. And the simplest, smallest type of convective cloud is the fair weather cumulus, which forms at the top of a buoyant updraft, which rises from the boundary layer. And the cloud forms when the rising parcel gets above its condensation level. So pretty simple. As we go up the chain, the next thing is the cumulus congestus, or as forecasters call it, the towering cumulus. This is when you have a lot of these buoyant parcels sort of all going up together, kind of in the same place, one after the other. The middle of the cloud becomes very moist, so the ones in the middle have a better chance of getting higher because they're not pulling in dry air. So you have
Bob,
this big.
I'm sorry again, Bob, but your share screen dropped out.
Let me see.
We can see it.
I could still see it fine.
Oh, okay. Sorry.
If anybody else has a problem, let us know. We don't want anybody left out here. So are you with me now, Gideon?
Yes, thank you.
Okay, so the cumulus congestus is when several of these buoyant elements get together all in one place and form a bigger cloud, which is more moist in the middle, so the middle part rises. The buoyant parcels can get higher because they're not pulling in the dry air. Once this towering cumulus reaches heights that are above the freezing level, then the upper part of the cloud becomes glaciated and it starts to form what we all call the anvil. Starts to take the shape of sort of the classic picture of a cumulonimbus. At this point, the cloud would almost certainly be raining, probably fairly heavily right below the middle of that cloud mass there. As we go up the scale chain, the next thing I would mention is the severe storm cumulonimbus. These are ones also called supercells. You've probably heard that term, probably just from local weather forecasters and so on. This is when the cumulonimbus becomes more organized and more severe. In this case here, this picture shows some hail there on the left and rain coming down on the right. And at this point, when the cumulonimbus reaches this severe stage, the airflow coming in from the boundary layer becomes quite organized and comes up this, puts in the left-hand side of the picture here. You can see how the cloud gets taller as the air comes in. The buoyant air is coming in this very organized fashion and forming a very strong updraft, which will reach all the way to tropopause height. That little puff at the top there is almost certainly overshooting the tropopause. It's also having hail and rain probably, and this is the kind of setup where you see tornado developing. This updraft, because these clouds form when the shear is very strong in a certain way, and that causes the updraft to be rotating as it goes up. And that rotating updraft is a favorable place for even smaller and more intense vortices, the tornado vortices, to form. And that would be right down here. And if you're a storm chaser, you know that you're trained to aim for this part of the cloud. If you've got clear skies like this and see the thunderstorm in the distance, you start driving really fast toward this part of the cloud. So maybe you get a picture of a tornado. But we're going up in scale here. The most extreme and biggest member of the cumulus family is our mesoscale convective system. Now, in that last picture you saw, you could roll down your car window and taken a picture of that cloud off in the distance. A mesoscale convective system is way bigger. The cold cloud here shown by the dark shading is the top of the mesoscale convective system. You can see it's about the size of the state of Kansas. So you would not be able to roll down the window of your car, look out the window, take a picture of this mesoscale convective system. It's just way, way too big. It's orders of magnitude wider than the cumulonimbus clouds. Not taller, but much, much wider. The other thing about these, besides the fact that the high cloud top extends over a huge area the size of a state like Kansas, the cloud is thick, so that you've got a lot of precipitation falling. And the microphysics of this precipitation process is actually quite interesting. I don't know if we'll get into that much today, but it is a very interesting problem. And these are also implicated in a lot of major flooding situations. They produce a lot of rain, a lot of water comes out of these things. This next picture shows a day on which there were 3 mesoscale convective systems. And there's kind of a funny story behind this particular slide. I like to keep using it because back in 2004, I was asked to give a talk on mesoscale convective systems. And I thought I would just look up some satellite pictures to show some examples. And I popped up in the current picture was this one here. It showed 3 mesoscale convective systems lined up in the central part of the country. So it made a nice little feature of that talk. But as you can see, there's 3 of these big cloud systems all going on at once, from Texas on up to Minnesota. But what about the rain? This same set of clouds. I also downloaded on that day in 2004. I downloaded the radar data that was active at the same time as that satellite picture. You can see the precipitation areas are shown in the bright colors. The greens and blues show the extent of the rain area. The reds and yellows show where, especially the reds, show where the precipitation is most intense. But what really gets interesting is if you look more closely at the radar. I just blow this one up. And the characteristic of these mesoscale convective systems is that they have 2 types of precipitation. That's why I mentioned the microphysical aspects of how the cloud particles grow and fall out. It is quite interesting because there's 2 completely different types of precipitation going on. The convective precipitation, that's where it's raining really hard. That's where you'd find hail. You might even find a tornado in one of these red elements. The whole thing is moving kind of from upper left toward lower right in this case, more or less. And the stratiform area, the stratiform precipitation is, you can see, quite a bit less intense. It's moderate precipitation, but it covers a big area and it accounts for quite a bit of precipitation. And in the tropics, as Gideon mentioned in the introduction, 40% of tropical rainfall actually comes from these stratiform precipitation regions. They're not quite as big in the mid-latitude areas because there's just more dry air, but they still probably account for 25-30% of the precipitation from these systems. I don't really have those statistics at hand. But the stratiform precipitation turns out to be a very interesting piece of the MCS picture. And it's always not neat and tidy. The one in the upper left here is kind of like the one I just showed you, has a line of intense convective cells followed by a stratiform precipitation area, moves down toward the lower right. And the picture is pretty much a leading convective line and trailing stratiform region. But this stuff these show up in all sorts of different configurations. If you look at a radar at any given time, you might see something like this, where the new cells are building off to the left and the stratiform is kind of offset to the right behind the older cells. sometimes it's just a big mess, it's just like a dog's breakfast here. It's just a mess, but everything's still there. There's still convective cells. There's still stratiform precipitation intermingled around in it, and both types of precipitation are present. It's just not quite as neatly organized. Kind of depends on, I mean, it does depend on how well this thing gets synchronized with the mid-level jet. I don't want to go into a bunch of theory here, but I do think there's one that's worth mentioning. And if you want to see details of this, go to my book, Cloud Dynamics, the second edition, chapter 9. Don't look at the first edition because I didn't have all this theory worked out in there in the first edition. But in the second edition, I do. And I think a key piece of theory comes from Mitch Moncrief, who found these pictures that you see in the lower part here. There's a big updraft and an overturning downdraft. These go across the scale of that whole big system. The convective cells will probably be embedded in here somewhere, and then all this is stratiform back here. This is another thing, shows the streamlines of the flow. It's the thing I wanted to emphasize is very, very deep. This is not just little boundary layer buoyant parcels. This is a whole whopping chunk of the lower troposphere going up in this system in a very systematic way. And what Moncrief showed is that, yeah, it's buoyancy that gets these things started, but when they get organized like this, they're not only overturning the buoyancy profile, but also they're accounting for the observed adjustment of the momentum in the environment, and they form in a typical sort of shear situation, and it's this balancing both the momentum and the buoyancy at the same time that seems to account for the fact that we have this larger scale circulation. And if you look at this picture, you see the smaller elements here embedded in the in this broad over ascending rear to front flow. The intense cells where all the hail and junk like that is happening is right in here. But there's also this not only ascending front to rear flow, but also descending rear inflow. And that's why I mentioned that it's when these things get in sync with a mid-level jet that they take on that more organized leading line, trailing stratiform structure. I've circled a couple of things here that I want to emphasize in the stratiform region. The stratiform region turns out to be not only interesting because of the precip, but also dynamically. At the base of this ascending rear inflow and the top of the ascending rear inflow and the base at the top of the descending rear inflow, you have a mesoscale low pressure system develop. Aloft, you have a high pressure system develop. So you have a almost nearly balanced cyclone here. And this was something pointed out by Mike Fitch, who was at Penn State back in the 1990s, and he showed that he first brought to attention to the fact that you develop this mid-level cyclonic circulation, upper-level anticyclonic circulation as part of a very strong mesoscale convective systems. And those have some dynamic implications for what happens to the large-scale environment and climate as a result of these mesoscale convective systems. So to answer that initial question, what is a mesoscale convective system? This is my definition. It's the largest of the buoyancy-driven convective clouds. It has a stratiform region accompanying the deep convective cells, and that's associated with the mesoscale circulation with a deep inflow, a meso low in mid levels, and meso high at upper levels, that last picture that I showed you. So that's my answer to the question that I was assigned. And I think what I'm supposed to do now is to move on to our next speaker, who is going to go into more details on the internal makeup of these mesoscale convective systems, and that is Dr. Rebecca Adams-Seelan, Senior Manager of Science and Atmospheric Research at the company called AER, Atmospheric and Environmental Research. They do a lot of research on all kinds of topics. Her interest is in these mesoscale convective systems. She leads a group concerned with the components and processes of these systems. Her mesoscale convective system research specifically includes microphysical processes and convectively generated gravity waves. A piece of the puzzle I didn't even mention here. She has identified gravity wave impacts on both the environment in advance of MCSs and on the evolution of the system itself using idealized simulations. And if I could editorialize, this is a very important and somewhat neglected topic, and I'm glad she's looking at it. She's looked at field campaign data, surface pressure networks, all kinds of stuff, anything she can get her hands on. And she really likes the bow echoes, which jump out in front of these squall lines sometimes. And she's conducted work observing and simulating gravity waves in conjunction with the bow echo development. And she's done all kinds of things. She's examined how perturbations to microphysical processes within the MCS, as I mentioned microphysics, how those lead to direct system modification and indirect modification through gravity wave generation. So these microphysical processes actually have dynamical feedbacks. And so with that, I will turn this over to Rebecca, also known as Becky to the rest of us. So take it away.
All right. Thanks, Bob. Okay. Is my screen successfully sharing?
Looks
I'm
good.
seeing it.
All right. Great. Okay. Yeah. Thanks for the great introduction, Bob. That's awesome. Yeah, and a good lead in. So yeah, I'm going to be focusing on just kind of two specific parts of MCS development and evolution. That's a big topic. So two specific things here. One really is the structure, say, of an MCS, and how does that structure come into being? How does it develop? And then number two, how can we really understand when we talk about, say, MCS strength or intensity? What do we necessarily mean by that? All right, so starting off with the structure of an MCS, I'm gonna use this handy vertical cross section here that I borrowed from the Washington Post, actually. So yeah, here's the ground. Here you go up in height, and you're kind of taking a cross section, looking through the storm at it. This here up at the front is that convective line part that Bob mentioned, and then here behind you might have a stratiform, kind of the less intense rain. And we will talk later, as Bob mentioned, there are many ways that this can kind of set up. This is sort of the most easily understood way, so we'll start here. When the storms first develop, you kind of get a cloud that looks, something like this. You get just a single updraft. Things are rising as the air cools within the parcel. You get rain condensing, and then it freezes. So you tend to get a lot of warmth right in the middle of the atmosphere. So if you think of latent heating, which results from phase changes, either condensation or freezing, that's going to tend to be maximized right in the middle. So here's latent heating with respect to height. And so you've got a lot of warming right in the middle. Depending on what your upper level environmental air might look like, typically it might kind of look like this, in that it's going to help blow some of this precipitation as it forms. It's going to maybe advect it backwards. So now you've got heavy rain kind of falling out more immediately, but some of the more lighter rain being advected rearwards. And then that can then fall out down below. Now you've got maybe warming aloft where some of this lighter rain is still forming or there's still freezing going on. But as that rain falls down below out of the cloud, well, now you have the chance for it to maybe evaporate, cooling by evaporation. It's going to melt probably too. So now your temperature profile, I guess you could say, inside the cloud is going to have two pieces to it. It's going to be warm up here, and then it's going to be colder down here. When you have a temperature gradient set up that looks like that, you're going to get a low pressure perturbation right in the middle. And as we all know, the atmosphere does not want a low pressure perturbation to exist and not respond to it. So you get a rear end flow jet flowing into the back of the system. So that is kind of how your initial wind flows set up. So you have air flowing in down at the surface, flowing out aloft, and then this rear inflow flowing into the back of the system and then descending as it goes towards the front. So yeah, that's one way to think about how that wind flow could have developed. But there are more ways, as it turns out. Let's say you take that exact temperature set of temperature heating profiles, where you have warming in the middle and then warming up top and cooling down below, where this is your convective line, and this is, again, your stratiform region. Let's say you just take that heating profile, you stick it in a model, and there's no rain, there's no precipitation, there's nothing going on at all. It's just the atmosphere is going to respond. It's going to make some sort of wind field in response to this heating. Well, this figure down here below is what that looks like. And this is actually from Bob's 2004 book, where you get a wind field that looks really similar in flow down at the lower levels, outflow back aloft, and then here's a nice rear end flow jet, and then subsequent outflow aloft. And that is simply generated entirely by gravity wave responses propagating out away from the system. So that's kind of yet another way that this same type of wind profile can show up. Well, it turns out there's yet a third thing that can be impacting these winds around an MCS. I think we mentioned the idea of a bow echo. What that is, again, you have your convective line here. But sometimes the middle part of that can get moving faster, and you could have it turn into what looks like a bow out of a bow and arrow. That can actually, you can generate some circulations on either end of this bow echo. These are called line end vortices, and that can intensify this flow into the system, that rear end flow jet into the system. So that's kind of yet another set of things that can affect MCS wind flows. And it turns out that this actually becomes even more complex as these things continue to evolve in time. You can get mid-level convective vortices that can become very long-lived. If different things line up, these things can actually last for even a day or two, and subsequently generate more convection. This vortical flows tend to be fairly complex as well. But then one more thing, one other way that winds can impact MCS structure, and that's just the environmental winds, particularly up at upper levels. So there are kind of some archetypes that have been mentioned about where the stratiform rain can be in relation to the convective line. Say if it's behind it, trailing stratiform, or it could be ahead of it, it can lead it, or it can kind of be parallel to it. So this makes it all look nice and simple. Of course, if you look at it in real life, it's never quite as nice and simple as that. But the general things apply. There's some convection, there's some stratiform rain, and the stratiform rain might be located in different places around that convection. And there could be a variety of different reasons for that, as we've seen. But one of the reasons is probably the upper level winds. This is from that Parker and Johnson study. They looked at, here are kind of the storm relative environmental winds that are perpendicular to the line, here on the left or on the right, and then parallel to the line. If you have trailing stratiform, you're much more likely to have kind of some weaker winds aloft. Leading stratiform, you're going to have stronger winds aloft that help advect the stratiform precipitation out ahead of the system. Parallel to winds blow parallel. All right, so that's, by my count, I think 4 different things ways that can control and modify the wind structure within an MCS. We've got the temperature perturbations due to microphysics. We've got gravity waves. We've got environmental flows. We've got vortical flows, and of course, all to make it even more difficult, all these things will, some of them will generate each other. Some of them will modify things that will then generate themselves. So there's this very complex interplay of how the wind flows within an MCS happen. All right. So now that we're good and confused there, and next step is that how can we understand MCS strength and or intensity? So this is actually has turned out to be a more complicated than you might expect. One of the ideas that has been around for a while is this idea of an optimal state. And that is, looking here on the left, if you have an updraft forming, you're going to have rotations on kind of circulations on either side of that updraft that are just caused by the updraft moving up through kind of stiller air. If you have any sort of low-level shear, you will get some rotation or kind of vorticity due to that low-level shear as well. If your vorticity values don't quite balance, it might act to tilt the updraft in one direction or another. So in this case, our low-level shear vorticity is kind of on its own, so it's helping to tilt the updraft back over it. Now, let's say our updraft actually starts forming some rain. Now you've got evaporation. It's cooling the air below the clouds, so you've got kind of a cold pool. Well, that has vorticity due to it as well. So the idea here is that if you can get the vorticity due to the low-level wind shear and the cold pool to exactly balance, your updraft will be upright. It won't be tilted one way or the other. So some theoretical work here on the right, don't want to get too far into this, but essentially, if you take the same amount of temperature perturbation and you have it be located straight up and down, as here, versus being slanted and spread out sideways, diagonally here, your pressure perturbations are stronger, and so your updraft speed is stronger. Now, something to keep in mind, though, this is all pretty theoretical. It's also pretty simple. You might remember we talked about a lot of different things that can affect MCS wind flow. What about, say, wind shear over deeper levels? Bob mentioned some, overturning, and there's been other studies that have seen similar things, where if you have wind shear that extends, maybe more of the depth of the atmosphere or troposphere, you can help tilt your updraft back more upright. When your rear inflow jet starts happening, that adds another source of vorticity to this vorticity balance equation, and that can help tilt the updraft one way or another as well, depending on if it tends to stay aloft until it gets pretty close to the updraft, or maybe it descends to the surface some ways behind the updraft. Interestingly, when it comes to a bow echo, we would probably consider these pretty intense features. They're frequently associated with severe winds. But in this case, they're also associated with a rear inflow jet descending to the surface and a really strong cold pool. So that would seem to indicate that you can still get severe impacts at the surface, even though maybe it's technically a suboptimal state where your updraft isn't exactly right up and down. That maybe means that this whole idea of optimal doesn't make a ton of sense. When we say optimal, is this to create kind of this our optimal framework for how this is working, or are we really mostly concerned at the end to what kind of surface impacts this is going to have, like how much rain or how strong the winds are. So this is just a plot, and it's actually some work by Dave, who'll be talking next, of max surface wind speed, and then this ratio between these two different vorticities from the cold pool and the low-level wind shear. If those are balanced right at 1, in theory, that's when our system should be most optimal, and you'd think we'd see kind of some of the strongest responses. But that doesn't necessarily correspond to where the strongest surface winds appeared. And in fact, some of the other results out of the paper kind of agreed with that. Actually, this has been quite the debate in the literature. It was originally published in 1988, called RKW theory, based off the 3 initials of the original writers. And there's since been a revisited version, comments on it, a reply to the comments, and then some additional things since then. So it's still an ongoing topic, but I think what we can all generally say is that yes, we can use these ideas of balancing vorticities as a framework to understand how the updraft might be more upright, but that doesn't necessarily translate to the strongest impacts at the surface, or necessarily longevity of the system. Right, so I guess my end takeaway from here is that MCS research is an active and exciting field because there's still a lot we don't know. It's surprisingly complex, and there's when you dig into things, it turns out that there's a lot of different physical processes going on. So hopefully you can maybe join us in our research.
Becky, if I may.
Yes.
There's a question by Bob Goldhammer on the Q&A. He says, in trying to explain meteorological terms to the general public, what would you say are the major differences between an MCS and a derecho? The use of the term bow echo would seem to blur the difference.
Good question. So I'm gonna say that if we use the parallel here of a square and a rectangle, I'm gonna say we would consider MCSs rectangles and then derechos squares, in that derechos are also rectangles, but they're a special kind of rectangle. So derechos are MCSs, but they're a special kind of MCS that produce extremely strong winds and last for an extremely long time. You're right that bow echo does kind of blur the difference a bit in there. That's really a way to describe the way something looks on radar, and it's usually associated with strong winds, but it may not be strong enough to be, say, a derecho, for example. Does that answer your question, Bob?
I don't know if you're talking to me, but I would agree, Becky. And also another way to think of it is MCS is a more general term. Derecho is a more specific type of situation associated with an MCS. Anyway, that would be my response.
Yep. Agreed.
Yeah, so Gideon, are we ready to move on?
I do believe so, Bob. Thank you.
Okay, our next speaker is Professor David Stensrud, who has been a professor of meteorology in the Department of Meteorology and Atmospheric Science at Penn State since 2014, but he has had a much longer career in these matters, working with NOAA at the National Severe Storms Laboratory, where he explored the benefits of short-range ensemble forecasting for severe weather prediction, and was the first manager of the NOAA Warn On forecast program. He's just been in this game for a long and important time. He received his if you want to know all this. He received his BA in math and meteorology from the University of Wisconsin at Madison, and his MS and PhD in meteorology from Penn State University. So he's kind of come back home to Penn State. Perhaps most importantly, for all of you viewers and listeners to know, David is the current president-elect of the American Meteorological Society.
Well, thank you, Bob.
With that, take it away, David.
Yeah, thanks for that nice introduction. Let's see here if I can share my screen and we'll get going. All right, so that look all right?
Yep. Looks good, dude.
Excellent. Okay, let's see if I move this up a little bit. All right, so I've been asked to talk about field experiments, numerical models, and forecasting, which is a fair amount. So we're going to get going and move through this. So Bob showed one of these. So I think we're all used to seeing, in essence, these mosaics of reflectivity observations from the WSR 88D network or the NextRad network across the United States. And they are spectacular. They are great for seeing MCSs. You know, here we have this MCS here in Oklahoma with this Boeing convective line, stratiform, and maybe even some active cells behind it. They can tell us a lot about where storms start and where they finish. But if you think about it, it's really a limited set of information. I mean, we don't know what's going on in the environment ahead of the system and how it might be changing. We don't know a lot about the wind field within the MCS itself. And so for decades, our community with, certain principal investigators have put together field campaigns where we go out and we take additional observations. And that's been done in the tropics and in the mid latitudes. And a lot of times, sort of the workhorse for all that data collection is the Ray 1 sonde or the weather balloon, which may be launched at much more frequent intervals than we typically do, for routine sampling of the atmosphere. Radars will be involved, so we actually can see what's going on. Initially, those radars were reflectivity only, and of course now they'll likely be Doppler radars or even dual polarization Doppler radars. And it might be over a network. We could use aircraft. And so it's really evolved over time, all these different field campaigns that we've done. And this is just a sample of where people have gone. So Gate was mentioned earlier, which was over the Eastern Atlantic. We've had a lot of field campaigns in the United States. I list a couple. These are all the acronyms for the field campaigns. But there are many more over the US. As you can see, Central America, South America, Western Africa, Europe, Indian Ocean, the Western Pacific, Australia. I'm sure there are field campaigns in Eastern Asia. I just didn't find them easily. So we do this because it helps us to understand more and more about mesoscale convective systems, their variety, the forces, the physical processes that lead to their development and evolution. So it's been an important part of that. And I just wanted to highlight one technological advance, because a lot of times as technology evolves, the field takes or makes use of that effectively. And of course, one platform certainly is aircraft. So this is, as you probably know, NOAA's P3 aircraft. There are two of them. If you look at the picture here, on the belly of the radar is this little black oblong shaped object. This is a belly radar, so it's scanning horizontally, which is helping the pilots, of course, in terms of where to fly the radar to stay safe. But also we're collecting data as that goes. But the interesting advance is actually on the tail of the aircraft, because as you notice over here, it has this little extension, which you typically don't see on the majority of aircraft. And this is called a fore-aft scanning Doppler radar. And so on the left here, you have a picture of the tail of an airplane with, in essence, the shell of it taken off. And there are two radar dishes. They're each about 1 meter in size, roughly. And one is tilted 20 degrees towards the front of the aircraft, and the other is tilted 20 degrees towards the rear of the aircraft. And when this is operating, this dish will spin. And as it spins, then it's sampling, in essence, as the radar also, or as the airplane is flying, the beam that's pointed towards the front of the radar is scanning in this direction towards the front at a 20-degree angle, and the beam that's behind the radar is scanning towards the back, also at a 20-degree angle. And so there's a time difference because it takes a while for the radar to scan here, then move to this location and scan backwards. So they're not quite at the same time. But with the Doppler radar, you basically have information, along those radials. And when you combine those, you get the two-dimensional wind field. And you can do this at various levels. And from that, then, we can actually fly the aircraft. And here are examples from the BAMEX field experiment, BOECO and MCV experiment in 2003. You can see the P3 flight path in the red. And then what we see are reflectivity from the radar. And then we also see the wind vectors. So the two-dimensional wind field is then displayed as well. And these are all from the P3. So if you look on the left image, it's about 8:10 in the evening. And the right image is 50 minutes later. And we can see the MCS has evolved so that it has one of these anticyclonic line end vortices that's formed on the left-hand side of the image here. And so the P3 provides this really unique data source that has been used very effectively to study convective systems. But of course, the P3 is one aircraft, or maybe if there's even two of them out there, it can only do so much. It will pass, either through or behind the MCS and has to turn around and come back again. So we're getting these snapshots of basically the flow field within the MCS. And so sometimes to fill in essence, those data gaps, we can turn to numerical models. So numerical models, of course, are created by taking the equations of motion. We convert them into an algebraic form that can run on a computer. You give the computer an initial condition, so a three-dimensional picture of the atmosphere, and then the numerical model will step that initial condition forward in time. And part of that process also is, no matter how you set up the model, whether it's grid points, it's finite volume, it's spectral model, at some point you have a certain spacing between your data points, what we call grid points. And a lot of physical processes in the atmosphere, and these are listed in this box, we don't represent directly on the model. We actually have to parameterize them. Things like radiation from the sun and from the atmosphere, but also the microphysics, so the creation of cloud water and rainwater and ice and snow and graupel. All those are parameterized because we don't predict every single particle. That's just well beyond us. And so numeric models then can be used and to also study mesoscale convective systems. So here's an example of the super derecho from 2009. It first forms over here in Kansas, develops in this nice convective line, which then starts to change direction and pretty much moves more eastward. We have this cyclonic vortex on the northern end. And of course, it was long-lived. It also produced quite a bit of severe on this particular event. And so here from the SPC, we have on the top, we have the severe reports. You can see the blues are the damaging wind, green are hails, and we have tornado reports as well across 3 states. Here from the SPC, are the hourly reflectivity above 40 dBz, where you can see how the line is formed and moved across. And then so what was done is Tom Galerno and Morris Weissman then did a numerical simulation. So they used a numerical model to simulate this event. So basically a simulation is looking at an event from the past. And then the idea is that if the model does a good job at representing, replicating what was observed, we basically can dig into the model then to try to better understand what's going on. Because with the model, we have output every few minutes at every grid point. And so we have very fine resolution in space and in time. And from that, we can diagnose the physical processes. And that in this case, they're basically asking the question, what's leading to the intensification of this cyclonic vortex on the north side of the convective system? And so they were able to diagnose from the model that if you look on this left-hand figure, that basically the spin, the vorticity in the cyclonic direction was increasing in low levels and increasing basically kind of in the upper part of the atmosphere. And they did some diagnostics and found out that it was a tilting. So basically vorticity that is spinning and gets tilted in an updraft that contributed to some of the enhancement of vorticity aloft and also stretching. And so models can really help us understand and get to the heart of these questions around what physical processes are leading to the behavior that we see. But it's really helpful to have all the observations to solidify what we see in the model, to verify what we see in the model, and to actually help us design the model simulations so that they, attack the problems of interest. And of course, models also are used to forecast. And so just one other thing I want to say is, we have these physical process schemes and models. They really play a critical role in MCS formation evolution. And so here I have in the upper panel, here in the center is the observed composite reflectivity for this particular day and time. And then on the left, I have basically, again, radar reflectivity from the model simulations. And the only difference is the microphysics scheme. So how it handles, the creation of rainwater and snow and ice and gravel. And you can see they look fairly different, at least in the specifics. Now, overall, the convection, the MCSs are in the same rough place. There's a lot of agreement in that, but the actual details are quite different. And so that's another challenge that we have, and an opportunity is how we improve these schemes for use in our models. And so I guess in summary then, field campaigns are incredibly important for helping us increase our understanding of convective systems and the processes that basically control their evolution. And numerical models are another key tool that we can use to study past events. And of course, we use them all the time, every day in weather forecasting. And with that, Bob, I will turn it back to you. Looks like you're on mute.
Bob, you're still muted up.
How many times have I done that? Okay. Our next speaker is rather special to me because I had the pleasure of being able to work with her for a few years. Ruby Leung has long been a scientist at the Pacific Northwest National Laboratory and is nowadays chief scientist of the Department of Energy's Earth System Modeling Project, which is a huge, big climate modeling effort. Just to interject here, why was I working with Ruby? Well, during the late 2010s, I guess, or something like that, I spent several years working at Pacific Northwest National Lab in the same lab as Ruby, and we had many exciting and interesting conversations during that time. I know most of you associate me with the University of Washington, but I also did have this side gig at PNNL. Anyway, back to Ruby. Her research cuts across multiple areas in modeling and analysis of climate, water cycle, and extreme events. It's pretty mind-boggling what she does. Her team has developed software for tracking MCSs and observations using, among other things, data from the TRIM and GPM satellite, or I guess the GPM satellite. But she's primarily known for the model simulations, I think. Anyway, using this tracking has helped with, as David just mentioned, has helped tremendously with the developing of the modeling and analysis tools that she and her group are using. They study the characteristics of MCSs, their interactions with the large-scale circulation of the climate, their roles in land-atmosphere interactions, their impacts on flooding, and their response to climate change. You might think she has a large group, and she does, because they do a lot of things. She's a member of the National Academy and has been honored in many different ways. She's a Department of Energy Distinguished Scientist Fellow and received the AMS's award for hydrological sciences back in 2022. So with that, I will hand this over to Ruby.
Thank you so much, Bob. And it was really a pleasure to have the chance to work with you, learn a lot about MCS from you. So, all right, so I'm the last speaker, and I'm going to be talking about climate change. So let me make sure my screen sharing is okay.
Looks good, Ruby.
Okay, good. All right. So as I said, the topic that I was asked to speak about is climate change influence on MCSs. And so I think there are three questions that we can try to answer here, right? So the first question would be very relevant. So you might ask, like, why climate change might be influencing MCS, right? So we need to answer that question. And then secondly, since we have all been finding that climate has already been changing in the past, so if that is the case, and if climate change can affect MCSs, should we have been seeing MCS changing already, right? So the second question is, have MCS been changing in the past? And then, or we also wanted to know, like, how might MCS be changing in the future? So these are the three questions that I'm going to very briefly answer in this short talk. So the first one, why can climate change influence MCSs? So the previous speakers really made my job much easier because they already explained to you what MCSs are and what influences MCS. But I just want to here emphasize again that MCSs develop in some environments that are favorable for them to develop. So these environments could be large scale, but it could also be mesoscale. So I give some examples over here. Like definitely in order to develop MCSs, you need to have warm and humid environments that provide a lot of energy. So this type of energy is what we call convective available potential energy, or CAPE. But generally, you would also need some lifting mechanisms. So we find that over the central United States during springtime, some large-scale synoptic forcing can provide that kind of lifting mechanisms. And then also particular to the central United States, so we know that this region is very much influenced by the Great Plains low-level jet. So the Great Plains low-level jet transport a lot of moisture, and so at the terminus of the Great Plains low-level jet, it causes moisture convergence. So the moisture convergence can destabilize the atmosphere, so that can also be very helpful for the development of MCS. And then, of course, there are also some subsynoptic scale type of perturbations that can help support MCS initiation, particularly in the summertime. Like, for example, some eastward propagating waves could be very helpful for that. So now back to the question then, why can climate change influence MCSs? So the answer would be that, well, I mean, these favorable environments, whether we are talking about the large scale or the mesoscale, could be altered by climate change. So I'm just going to give you two examples, which in the larger sense, we need to recognize. So the first one is that under global warming, not only that the temperature is increasing, but the increasing temperature can also increase the amount of moisture in the atmosphere. So combining the temperature and the moisture, it would be very easy for us to look at this using a quantity called equivalent potential temperature, which account for both the thermal energy and the latent energy related to the moisture. So here, this figure basically shows that CAPE, which I already talked about, which is the type of convective energy that is really needed to have MCS develop, really strongly correlate with the equivalent potential temperature. So if you look at it globally, this correlation in most area, including both the land and also over the ocean area, reaches a correlation of almost like 0.6 to 0.8. So then if we expect that under global warming, both temperature and moisture increase, and therefore the equivalent potential temperature will increase, then the CAPE will also increase. But the story is not that simple, because there is actually a bit of a tug of war going on. So besides the increase in the CAPE, which is the energy needed, we find that under global warming, a really robust response to global warming is that over land is actually going to be getting drier. So if you look at the near surface, in terms of the surface humidity, relative humidity, in most areas, such as the Amazon, the central United States, and in many other land regions, the surface relative humidity will actually be decreasing. So this is what we call increased land aridity under global warming. So as you can imagine, if near the surface, the relative humidity becomes drier, so this is actually not too good for the buoyancy, right? So then it can actually suppress convection. So now you have two factors going on, the increase in the CAPE, but also an increase in the what we call convective inhibition, or the SIN, which is related to this reduced relative humidity near the surface. So at the end, what is going to happen is what we really need to talk about in terms of like how MCS may be responding to climate change. So my second question, as I said before, if climate has already been changing and we know that the temperature has been increasing, so have MCS already been changing in the past? So there are quite a few studies that have started to look into this. So one of the studies is published by our group. And so we look at the MCSs during springtime over the central and the eastern United States. So looking at the past 35 years using observation data, we track the MCSs. We find that if we look at two quantities at least, like for example, the first quantity is the lifetime of the MCS. How long do they last? And we see an increasing trend over the last 35 years, suggesting that MCS have been lasting longer over the central United States in the last 35 years. Another quantity that we have been looking at is the 95th percentile exceedance frequency, right? So the amount of precipitation, particularly these extreme precipitation produced by MCS, has also been increasing, as you see, mostly green in color, which is the positive, right? So yes, over the central and eastern United States in the last 35 years, there have been evidences that MCS have been lasting longer and become stronger in terms of producing heavier precipitation. So there have been also other studies. For example, one study looking at extreme storms, MCS storms over the Sahara, and they found that since 1982, the frequency of these type of extreme Saharan storms has already been increasing, and in fact tripled the amount. So it's a very significant change. There has also recently been another study that I'm involved with where we look at MCS frequency as well as the precipitation over Asia. And we find that between 2001 and 2020, these quantities have been increasing over East Asia, but not everywhere. They find that actually they have been decreasing over South Asia. So this is another factor that we also need to consider. So now back to the third question. So how might MCS be changing in the future? So in this regard, models are really important for us to look at how MCS may be changing, because MCSs, they form in very different types of environments, and there are many processes controlling their development. So models really can allow us to, if we can resolve the convection, they can be very powerful tools. So we can combine models together with theories to try to address this question. So one of the earliest studies that look at this indeed use very high resolution climate models. So these are regional climate model at 4-kilometer resolution where MCSs can actually be simulated. And in this study, they find that indeed under global warming, the CAPE will be increasing in the future, but then indeed the convective inhibition, which is related to the reduced near surface humidity, will also be increasing. So the two factors combined together means that for weak convection, the convective inhibition is going to suppress that kind of weak convection. But then if you have enough CAPE, the suppression is not going to suppress the convection for very long. And so when there is enough energy, the convection can actually become very explosive and cause stronger MCS and producing stronger precipitation. So this study, the two studies use the same set of simulations. They do find that indeed the MCSs that they've seen in the future compared to the present day, it produces more precipitation and the precipitation area will become larger. So these are some of the earliest studies that look at MCS and how they might change. So recently, we have also published another study where we particularly look at a cluster of MCS events that happened in 2015. So these sequential clusters of MCS events happened over Texas, Oklahoma, and produce record-breaking flood events over there because like so many of them just passed by within like 2 weeks or something like that and produce a lot of heavy precipitation. And so what we did is we used a model that can resolve this kind of processes. We simulate this particular sequence of MCS event as happened in the past in 2015. And then we impose changes in the environmental conditions like warmer temperature and increased moisture and simulate it again and see how they might change in the future. So just to briefly summarize what we found. So we found that under global warming, if we look at the updraft will become 25 to 100% wider, and also the updraft can become stronger. So this is the convective part of the MCSs. But as Bob and others already mentioned, the MCSs is not just about the convective core. It has the endfold part, which actually produce a lot of stratiform precipitation. And there is also downdraft associated with it. And when we look at the downdraft, we also find that the downdraft will become wider as well as stronger. So you can imagine like stronger updraft as well as stronger downdraft. All together combined, we see that in the future, the rain volume will increase by roughly 50%. So the convective area will increase and the stratiform area will actually shrink. But altogether, there is more convective rain compared to the stratiform rain, but combined together, the rainfall volume will increase by 50%. Another example that takes us to another region, and now I'm going to come back to the United States, but I find that because MCS is so important in other regions as well, so I'm going to show you one other example, which is over the Amazon basin. So in 2005, in January, there was a really big squall line that swept across the Amazon basin, uprooted a lot of trees over a large area in the central Amazonia. So we also used a very high resolution model, simulate this squall line, and you can see it compares really well with observation shown by the LA5 data when we look down like a satellite, look down from above. And what we see is that if we impose changes in the environmental conditions to see how it might be changing in the future, we find that the strong winds associated with the squall line doesn't necessarily increase by a lot, but the size of the squall line increased by almost 10 times, suggesting that if the same storm is going to happen again in the future, the areas where the trees would be uprooted by the squall line could become almost like 10 times as big as what we might be seeing in the past. So now, as I said, we come back to the central United States. Here, just the last example, in 2012 of June, there was a North American derecho that's really swept across the country, causing a lot of power transmission infrastructure damages and things like that. So again, we use a very high resolution model and successfully simulated this derecho. In fact, getting wind speed of the order of like 30 meters per second. So the severe winds associated with this derecho can be well simulated. And then again, we simulate this storm as happened in the past, and then look at how it might be happening in the future. But surprisingly, for this particular derecho, so here we see the simulation of the derecho as happened in 2012. So it swept across the country, a lot of reflectivity showing strong convection going on. But when we look at it in the future, actually the size of the derecho actually shrank by quite a lot, and also it dissipates much earlier in the future. So it is not one size fit all. because as previous speakers have already also talked about, these storms, they develop in different environments and there are many processes governing them. So not every single storm would be increasing in strength or the size in the future. But generally, we do see that for score line and MCSs, it's more common to be seeing under global warming that they would be intensifying. So now just answering the questions again, why can climate change influence MCSs? The answer, if I put it in a very simple way, is that climate change can change the large scale and or the mesoscale environments, and therefore they can change MCSs. Have MCS been changing in the past? There are some observational evidences that MCS frequency and intensity have increased in the past few decades, for example, over the Sahara region, over the central United States, but not everywhere. And I think partly we also need to recognize that there is a lot of natural variability going on. So what happened in the past is not only affected by climate change or the anthropogenic factors, but the natural variability should also be accounted for. And then lastly, how might MCSs be changing in the future? So we see that MCS environments will generally become more favorable because of the increase in the Cape. And then even the increase in the sea potentially suppress weak convection, but it keeps more moisture in the boundary layer that can help the strong MCS to become even more explosive in the future. But then there are also many other countering effects as well. So it's a more complicated question. So it really takes more researchers, and I hope you get interested in this topic to continue to look into this further. So with that, thank you for the time and the attention.
Actually, Ruby and Bob, if I may interrupt, there is a question that came up from Aaron Wang, and I want to put this out there. Aaron says, not sure if this is related, but why do they often talk about a trough in the jet stream, which is an area of cold air pushing south, as having low pressure / stormy and rising air? I thought since cold air sinks, it would be high pressure.
I think this question is probably for Bob because he talked about the mid-level anti-cyclone and the upper level anti-cyclone.
Yeah, I'm going to read the question again.
Thank you, Ruby.
Yeah, this is not a straight. There's not a straightforward answer to this. I can understand why you might be a little confused by the terminology, but a trough in the jet stream is where, due to some wave instability in the jet stream, it develops a trough and a ridge, so it just bends back and forth. And in the trough areas, you get a sloping area, low pressure area, and it has to be analyzed in terms of I'm trying to think of a way to do this without getting too technical, but there are yeah, see, Dave's smiling. I think I might turn it over to him in a minute, but yeah, the jet stream folds into this trough-shaped configuration, and it has to be looked at in 3 dimensions. And when you look at it in 3 dimensions, you find that there's a low-pressure system that slopes back toward the west in the mid-latitudes, and it forms from a process that's called baroclinic instability, and it's not a simple matter of a cold air rising, or warm air rising, cold air sinking. There's certainly cold air that sinks, and there's warm air that rises involved, but you know, without going into a lot of dynamics, I think that's the basic thing to say. It's part of this process that we refer to as baroclinic instability, which is kind of an advanced topic, but at least but at least to these sloping low pressure systems, the trough is really only, it's a three-dimensional phenomenon, and it can't be thought of just as what goes on at one level. It's highly three-dimensional. It's manifested as a low and frontal system at the surface, and a trough at mid levels, and they're connected through in the vertical. And without getting myself any more tied up in knots, I think I'll leave it at that, and David can add or not if he wants to.
I think one of the ways I think about it in very simple terms is you have an upper level trough. Typically to the east of that, you have warmer air at the surface. And to the west of that, you have cooler air. And so to the east of the trough is often then when we have, what we call, stormy weather can occur just to the east of the trough where the low pressure system sets up. And it's all, very three-dimensional. The warm air at the surface doesn't necessarily correlate to warm air aloft. And so it does get into a lot of dynamics, as Bob said, but that would be perhaps a simple way to think about it.
Yeah, that's good, Dave. And that warm air at the surface is what meets up with colder air at the front and can trigger things like MCSs if the contrast is strong enough. And that's all connected with this trough that you see aloft.
Thank you, Bob. And then
that's the best we could do with that one.
Hey, no, I won't even pretend to know what's going on. So I am here though to present questions, and we have another one here. This one is from Leonard Simmons. Sorry, Leonard, if I messed that up. Leonard asks, can you quantify the degree of model uncertainty in forecasting future MCSs?
Yeah, so I guess maybe I'll take this question. Certainly, model has a lot of uncertainty, as we have seen, for example, from CMIP6 or that type of large-scale global models. So they do have a lot of uncertainties, both in terms of like simulating how the environment may be changing in the future, as well as simulating the structure of the MCSs themselves, which could be related to, for example, uncertainty in the microphysics and all these different processes that David also talked about, right? So in that regard, we do really need to account for the model uncertainty in looking at how MCSs may be changing in the future. Just want to summarize again the two aspects. One is how the large-scale environments may be changing. So model uncertainty can affect that. And then the second part is the MCS structure itself, and the model uncertainty can also affect that. So both of them are important factors to consider when we look at model uncertainty and projecting future changes.
Thank you, Ruby. Oh, and we just got another question popping up here from Mustafa Kamal. Mustafa says, what is the single most key difference between U.S. Great Plains MCS and East/South Asian MCS?
Well, for one thing, the East and South Asian MCSs have been studied far less than the others, so there's less to go on here. But being that East Asia is still mid latitudes, and these storms would be associated with the mid latitude jet stream, I would think that, my guess is they'd be fundamentally rather similar to what we see in the U.S. As you go to South Asia, especially south of the Himalayas, it gets more complicated, and MCSs are actually less common there, but they can be triggered either over the Tibetan Plateau or even in the lowlands south of the Himalayas, if the flow from the Bay of Bengal the moist flow from the Bay of Bengal can flow in and strongly enough to in other words, monsoon low has to kind of get stretched out to the east to bring a jet of warm air in. Then it sort of becomes a little bit like the story that Ruby was talking about with the low-level jet next to the Rockies, but that doesn't happen very often in the case of South Asia. But it does happen, and we have seen even squall line with trailing stratiform precipitation south of the Himalayas, but it's pretty rare, and we haven't had many tools to study these things yet. We mostly have some case studies from things like the TRIM satellite. So there's more to learn there, but I think those are the main things. The South Asian ones are very different animal from the ones in the East Asia. I think East Asia is probably not a whole lot different from the U.S. I don't know. What do you say, Ruby?
Yeah, and I'm not so sure about the key difference, but certainly, as Bob said, there are some differences, but also actually quite a lot of similarities as well. Because even in East Asia, the low level jet also plays some important role in the formation of the MCSs. But then even when you're talking about the MCSs over East Asia, it also depends on whether you're talking about the central part of China versus like the southern part of China, where the land sea difference is causing a little bit more or having a little bit larger role compared to the central China, where a lot of it is really related to the Meiji front system. So in a sense, I think there are so many unique, or even within a big region, there are differences in the environments that can cause differences, even within like East Asia or within the U.S. alone. The southern Great Plains and the northern Great Plains actually also a little bit of difference as well. Yeah.
Yeah, and reading Mustafa's question again, Ruby and I are answering largely in terms of environmental differences between the two regions, but I think his question was the difference between the Great Plains MCSs and MCSs in other places. And I think fundamentally the same types of environmental features have to come together in order for these things to break up. And then the net result is rather similar phenomena in all these different places, but different environmental conditions can make those arise in different places, either less or more frequently, or in slightly different configurations with the convection and stratiform maybe arranged differently and that type of thing. But basically an MCS is an MCS, and there's a lot of different environments that these can occur in.
All right, thank you, Bob. Thank you, Ruby. I think that's the last question that we have. Ted, did you have anything that you wanted to add question-wise before we wrapped up? I know we completely overshot our time goal here, but you know what? That's okay, because everybody's sharing and learning, and that can't be a bad thing, right? But yeah, Ted, do you have anything for us?
Yeah, we haven't lost too much of our audience.
Oh no, they're sticking around. That's cool. Thank you, audience.
I think this was great, and I guess the one thing I would ask, maybe from the enthusiast perspective, we're always wondering, what might we do in this grand scheme of MCSs to help contribute. It's always been a dream of mine to maybe participate in some way in one of these field projects, and I know that there's some mechanisms that we can be maybe indirectly involved. One of them that comes to mind is CocoRoss and rain gauge networks and reporting precipitation. Are there other things that we can maybe do as enthusiasts?
Well, Ted, one thing I'd say is be careful what you wish for, because yeah, it's absolutely fascinating and inspirational to be involved in these field works, but they are grueling and hard, and they wear you out. So you have to be prepared for that. But otherwise, I wish we'd have known you wanted to volunteer. We would have brought you somewhere.
Then you can also do modeling.
So I'll make a pitch for the MPEG weather app. So it lets you basically report what kind of precipitation is falling at your location. So, it could be reporting hail or rain, or of course in the winter it might be snow or freezing rain. And those are very helpful because getting precipitation type at the ground correct is still a challenge.
I'm sorry, David, what was the name of that app again?
MPEG, so MPING.
Thank you.
I'll
And
add
you download it
a
for free.
second recommendation for MPEG. That's a great setup. I'd also, if you're willing to call in reports to the Weather Service, severe wind reports are incredibly difficult to get, and really hard to standardize. So trying to connect our understanding of what causes, what about an MCS causes severe winds, that can be hard to do if you don't know where the severe winds are happening. So even just an old-fashioned call into the Weather Service can be a good one too.
Having an anemometer is always a handy thing, no matter where you are.
Fair, yes. Yeah,
Yes.
yes. That would be ideal, but even if it's just estimating off of damage, it's a little something's better than nothing.
Yeah, before we shut down here, I want to thank Gideon for helping us organize this thing today.
Oh,
It all came off just fine.
thank you so much. Yeah, it's a lot of time and effort and work that goes into putting this together from our panelists and our moderators. So we at AMS Weatherband absolutely appreciate every minute and all the effort that you put into this. So thank you.
Yeah, I want to echo that and thank all the panelists. Thanks, Gideon, for all of your help. And also want to recognize I'll call him my partner in this project, Rich Clark, who is on here with us, and was a fantastic support from the time we sort of conceived this idea together, and was very helpful in getting this all together. So thank you, Rich.
So how'd you come up with the name Weatherband?
That was before my time, Bob. I think I don't know, I really won't pretend to know how it came about, but I think it has something to do with the weather radio thing, and then also the sense of community. Everybody's in a band working together, and then it kind of branched out from there. Now we have solos where weather band members can contribute things, and we'll feature them as they're kind of like their time in the spotlight. So it's grown.
So I thought maybe just been a band of crazy weather nuts.
That might be the alternative
Could be
explanation.
I'm happy to be involved. Yeah.
We're going to do weather karaoke.
Okay, it's on, Rich. It's on next conference. We'll find some place, some venue. But all right. Well, with that being said, Bob, did you have anything else to say to wrap things up for the evening, or anyone else in the panel? And Rich and Ted?
No, it's been interesting. I'd never done one of these kind of things before, so it was new to me, new challenge. It was interesting, and I had to dig out all my old class notes and figure out what to say.
Thank you, panelists.
Yes. Yes.
Thank
Again,
you.
thank you, everybody.
Thank you, Ted and Gideon, for leading the organization on this.
Oh, shucks. Oh, yeah, y'all did the hard work. So yeah, thank you everybody for joining us. And I guess we'll just wrap it up. For the audience that's still remaining, again, many thanks to you for staying over when the bell rang and everybody else ditched. We very much appreciate your dedication to what we're doing this evening.